In this video, we'll explore the basic concepts of servo tuning within the environment of Sigma7 and Sigma1 Plus version 7. Hi, I'm Matt Pelletier. It will be to your benefit to understand the fundamental concepts of servo tuning before moving ahead to execute the tuning functions in Sigma7. To define tuning, we must talk about servo control loops and associated bandwidth. Then we'll outline the general tuning process and describe the three methods of tuning available in Sigma7. Finally, we'll discuss how to determine if tuning is even required at all and discuss mechanical issues that often seem to be tuning related. You won't need any hardware or software for this section. Let's just get familiar with the terms and concepts related to Sigma7 servo tuning. What is tuning? Tuning means optimizing how the amplifier responds to feedback from the load. It's all about moving not just the motor, but the entire servo mechanism in such a way that it is smooth and stable while still accurately following the controller's move profile. This is done by adjusting the gains and other parameters in the amplifier that affect how each control loop in the system responds to error. There are three control loops in the Sigma7 servo amplifier: torque, speed, and position. Which of these loops do you think has the fastest update? The fastest loop is the torque loop. It controls the amount of current in the motor and can also be called the current loop. It receives a torque reference command from the speed loop output, shown as point A on the diagram, and causes torque to be produced in the motor regardless of speed and position. The torque loop is tuned to the properties of the servo motor. How do we find out these properties? It's pretty easy. You don't have to. Since the motor is recognized by the amplifier through the serial encoder interface, those motor properties and tuning comes factory set. So there's technically no tuning required for the torque loop. However, filters must be set at the input to the torque loop based on the response of the connected load. This torque reference is produced by the output of which loop? The speed loop. The speed loop is like the cruise control in your car. It looks at feedback speed compared to commanded speed, and the difference between the two is sent through the gain parameters to output as a torque command into the torque loop. Now, what do you think? Would you tune the speed loop to the motor or to the load? You'll tune it to the load. You can graphically trace and monitor the speed reference and feedback speed to analyze that response. What letter on the diagram is speed reference and which is feedback speed? Reference is point C, and feedback from the encoder is B. Ideally, when you've tuned, the speed reference and feedback speed will very closely match. The reference to the speed loop comes from where? The position loop. The position loop calculates the position error between the commanded position from the controller and the feedback position from the motor. What letter on the diagram is position error? E is position error, and you see the speed reference command, C, is generated based on the error going through the gains of the position loop. The gain parameters of the position loop are also set based on the response of the connected mechanism. And again, you can graphically trace and monitor the position error directly, and also the speed of the reference command coming in from the controller. Comes in from the controller over Mechatrolink 3. Ideally, each of these three speed profiles, the command from the controller, the output of the position loop, and the feedback of the motor, will all match very closely. So all these calculations and all these commands are happening at the same time. Torque is the fastest, then the speed loop, then the position loop. Each of these loops has an associated bandwidth, meaning a maximum frequency response. The bandwidth can be determined by the settings of certain tuning parameters. You can also measure the bandwidth of the loop by commanding a sinusoidal waveform at the loop input, keeping the amplitude constant while increasing the frequency. Will the actual output match the input amplitude for all frequencies? No. There will be a maximum frequency at which the actual output amplitude is too low to be usable, or the output is too far out of phase with the input. That cutoff frequency is the bandwidth of that loop. Now, why is this important? Well, in order to maintain stability of the servo control system, you need at least 4 times bandwidth separation between the different loops. For example, if the position loop is 100 Hertz, what would the minimum bandwidth of the speed loop need to be? You multiply by 4 to get 400 Hertz. If this is the case, then what is the minimum bandwidth of the torque loop? Multiply 400 by 4, you get 1600 Hertz for the torque loop bandwidth. If you're setting servo tuning parameters, this means the sequence in which you set the parameters is critical. For example, you may want to improve the positioning response, so it seems logical to start by increasing the position loop gain. But what's wrong with that? Increasing the position loop gain may bring the position loop bandwidth too close to the speed loop bandwidth and result in vibration and instability. Instead, if you need to increase the position loop bandwidth, you first need to set parameters to increase the torque loop bandwidth, then the speed loop bandwidth, and then finally the position loop bandwidth. The good news is that you don't have to set these parameters one at a time and keep calculating the bandwidth. This is all taken care of automatically when you use Sigma7 Plus Advanced Auto Tuning and Custom Tuning functions. In these functions, you classify the rigidity of your mechanism, and this determines the required bandwidth separation factor, and you're able to set all of those parameters simultaneously. Well, that's all very well. How do you tune the servo system? The general tuning process is to start with a default tuning and command the machine to move what you would consider to be the worst case move profile. What factors might describe this worst case move? Well, for tuning, it means the highest acceleration and the highest speed. It's not the highest cycle rate because you do need to see how the motor responds after the move completes. So you execute this move and then look at the data trace of the actual response of the move and measure the graph to determine whether or not that response is acceptable for the machine or if improvement is needed. If you need to improve the response, then you can make some parameter adjustments, run the move again, and measure the response again. The tuning section of the product manual for Sigma7 outlines this in a flowchart. And you can see here, as soon as the response is acceptable, you're done tuning. This chart also lists the 3 main tuning methods in this sequence: the tuning less function, the auto tuning, and custom tuning. As you advance through these 3 tuning methods, there is the possibility of improved response, but taking increasingly more time to implement. The default tuning-less response is often sufficient, but if it's not sufficient, what's next? Move on to advanced auto tuning. If you still need better performance, then try custom tuning. Let's look at each of these 3 methods in a little more detail. By default, the servo is tuned with YASKAWA's proprietary tuning-less algorithm. Tuning-less emphasizes stability of servo response and immediately adapts to a changing load. In fact, the measured response is virtually identical for all loads up to a load-to-motor inertial ratio of 30:1. Can 2 axes remain synchronized with each other if they have different loads? With tuning-less active, yes, 2 axes can remain synchronized with each other even if they have different loads. OEMs find that tuning-less results in uniform and acceptable performance and will compensate for small mechanical differences between machines. Advanced auto tuning is an algorithm that automatically measures the servo response and iteratively makes tuning parameter adjustments while the machine runs a test move over a number of cycles. Advanced auto-tuning is also capable of detecting and applying advanced features such as model following control, vibration suppression, and anti-resonance. It's really an easy way to dramatically improve your machine performance when the load inertia does not change. And custom tuning gives the engineer direct access to the levels and filters of auto-tuning, and you can manually adjust them. Now, this is going to require careful measurement and analysis of the response, and a very good understanding of the machine and the process itself. Often, an increase in one performance measurement results in a decrease of another, and so an acceptable balance must be found by trial and error. So you can see that you don't have to go through all three methods for every servo axis. A point-to-point application, such as a case packer with changing load, would be a great candidate for tuningless. Advanced auto-tuning would be great for your typical actuators used in positioning applications. And for a demanding application like a high-speed labeler, you might have to go as far as custom tuning. Remember that for many applications, the factory default tuning, tuningless, will work just fine, and no further tuning is necessary. But what might you observe in the machine that does indicate tuning is required? Additional tuning may be required if the machine exhibits sluggish, slow response. You may also need to tune if you hear audible noise or observe vibration and oscillation. Some alarms such as overload, overspeed, or excessive position error can also indicate that tuning is required. If tuning is in question, the best recommendation is to graph the response of the machine and see what it looks like. In Sigma Win Plus, this is called data trace, which is a topic coming up in another video. Now, is lack of tuning the only reason why you might observe these types of behaviors in your machine? Before tuning, it is critically important to check the mechanical system. Attempting to tune away a mechanical problem will at best only result in a temporary fix. The squeaks and vibrations that you may attribute to servo tuning could instead be caused by a loose part somewhere in the system, such as a belt or motor coupling. It could also be due to friction. For example, a holding brake in the system is not disengaging. And maybe you hear the noise of components dragging against one another when they shouldn't, or that it's time for lubricant on the moving parts. The servo coupling between the motor and machine shaft is also critical. It must be within the alignment specifications. It really needs to be zero backlash, servo class coupling with high torsional stiffness, such as bellows, spider, helical, and there are others. A load of excessively high inertia can also make the system difficult to tune. Machine response can be improved in this case by reducing the moving mass or installing a gearbox between the motor and the load in order to reduce the inertia that's reflected to the motor shaft. A machine with tight, compact, solid, rigid build will be able to respond accurately to the servo system. Conversely, a non-rigid machine with mechanical compliance will require many filters in order to remain stable and will not be able to respond accurately. In short, do a reality check on the machine before you start to tune and try to reduce mechanical compliance in the machine wherever possible. In the upcoming videos of this tuning series, we will go through the entire tuning process in detail. Until then, I hope this introduction gives you the right background and perspective to know what tuning is and how it works with YASKAWA's Sigma7 servo. Thank you for watching this video. For more information on Sigma7, please go to yaskawa.com. Products, Sigma7 servo products.